Welcome back to Classical Mechanics. Now we are moving to the chapter 3. You are looking at a skier. This skier flying through the air shows an example of the motion in two dimensions. In the absence of the air resistance, the path would be a perfect parabola. The gold arrow represents the downward acceleration of gravity g. Galileo analyzed the motion of objects in the two dimensions under the action of gravity near the Earth's surface into its horizontal and the vertical component. We will be discussing how to manipulate the vectors and how to add them. Besides analyzing projectile motion, we will also see how to work with the relative velocity. These are content of chapter 3. We will start with the vectors and the scalars. They are the physical quantity describing the two-dimensional motion with the magnitude. And also we will find out how those vectors can be added or subtracted by using the graphical method. There are a lot of different ways to manipulate the vectors in two-dimensional motion. So we'll take a look at how it works. And part of this content, we'll go through the unit vectors and vector kinematics. And finally, this chapter will touch the concept of projectile motion. And also we will solve some problems of examples involving projectile motion as a large part of this chapter. And finally, we will look at the relative velocity as additional part of this chapter. Drawing a diagram of a particular physical situation is always helpful in physics, and this is especially true when dealing with the vectors. On a diagram, each vector is represented by an arrow. The arrow is always drawn so that it points in the direction of the vector quantity it represents. The length of the arrow is drawn proportional to the magnitude of vector quantity. For example, in this figure, blue arrows have been drawn representing the velocity of a car at various places as it rounds a curve. The magnitude of velocity at each point can be read off in the figure by measuring the length of a corresponding arrow and using the scale shown. So 1 centimeter corresponds to the 9 kilometer per hour. So when we write the symbol for a vector, we will always use the boldface type with a tiny arrow over the symbol. So for velocity we write the V. And if we are concerned only with the magnitude of vector, we will write simply the V in italics as we do for other symbols. Vectors are a powerful tool to describe the motion of the object in 2 dimensions or 3 dimensions. We'll take a look at how the vectors can be manipulated in their 2-dimension and 3-dimensional motion using the graphical method here. So we simply use the arithmetic for adding the scalars. Simple arithmetic can also be used for adding the vectors if they are in the same direction. For example, if a person walks 8 kilometers east one day and 6 kilometers east the next day, the person will be 8 kilometers plus 6 kilometers equals 14 kilometers east of the point of the origin. We say that the net or the resultant displacement is 14 kilometers to the east, as you can see in this figure. If one, on the other hand, the person walks 8 kilometer east on the first day and 6 kilometer west on the other second day, then the person will end up 2 kilometer from the origin. So the resultant displacement is 2 kilometer to the east. In this case, the resultant displacement is obtained by subtraction. 8 kilometer minus 6 kilometers equals 2 kilometer. But simple arithmetic cannot be used if the two vectors are not along the same line. So we will take a look at how those two lines are not in parallel, which means that the motion occurs in two-dimensional space. Suppose a person walks 10 kilometers east and then walks 5 kilometers north. Well, these displacements can be represented on the graph in which the positive y-axis point north and the positive x-axis point east, as described in this figure. On this graph, we draw the arrow labeled D1, and to represent the 10 kilometer displacement to the east. Then we draw the second arrow D2 to represent the 5 kilometer displacement to the north. Both vectors are drawn to scale as shown here. So the magnitude of this displacement is square root of d1 squared plus d2 squared, and direction is east to north. So that is resultant displacement, and that is described by this notation.